All right, thank you, Rupak, for letting me go ahead here. Sorry for the delay. What I was going to do is, I have to confess, when I built this up, I wasn't 100% sure completely about audience, time of presentation. So I only put about 80 slides together for the next 20 minutes, so we'll try to rip through those in reasonable time. Luckily, there's a lot of stuff I can skip. That's actually a joke. I don't have 80 slides. I guess I should start by saying what I'm going to talk about. So this, basically, what I'm going to talk about today is a new ECP project, and I think Paul Messina gave an overview on ECP yesterday. Is that correct? Okay, good. That means I can already skip my next two slides, which is good. So anyway, this is one of the application areas inside of ECP on basically doing operational performance on small modular reactors. I'll give a little overview of what small modular reactors are for those who do not know. Unfortunately, I don't know much about them either, I have to confess. So I'm more of an applied math, numerical methods person, working in the nuclear engineering and high performance computing space. But hopefully I know enough to give a brief overview. So we can shoot by these next two to get on track. And since these people probably mean nothing to you, I'm going to move by that. So what I'm going to do is talk a little bit about the motivation of how this project came about. In 2012, DOE put out an funding opportunity announcement with the goal of getting operational SMRs online by 2025. All right, what's an SMR? An SMR is a small modular reactor, and where traditional, I say traditional, but most of the big nuclear reactor fleet in the United States consists of almost all of them are basically built on light water reactor technology, which basically they use the light water, regular water as a moderator or reflector to keep neutrons in the core. I'll show you some details about that in a little bit. Ultimately, though, these are big facilities. All right, they generate many hundreds of megawatts of power. Along with, and they're just big, they're involved lots of licensing issues, lots of maintenance issues, and you've probably read in the news all sorts of stuff about how difficult it is and what a big capital cost investment it is to build a nuclear reactor. So the idea is that, you know, building in some sense on a decades-long history of building smaller reactors, particularly for things like the Navy, right? Well, can we maybe make a bunch of smaller facilities built on what are called small modular reactors? The idea being that they can get rid of these two big hurdles, these high capital costs and these really long construction timelines that are kind of limiting the large-scale implementations. This also kind of feeds in naturally to the way that electric utilities are going, where they're going to smaller, more agile, for lack of a better phrase, type of investment into many smaller power plants as opposed to really big multi-100 megawatt electrical plants. So they're very similar to what's the most common type of nuclear reactor in the United States, which are pressurized water reactors, which basically use a four-cycle steam line to basically heat steam, and they're done at pressure, so everything stays water. Okay, until they hit the actual heat exchanger, but they're roughly a quarter the size. All right, so they're roughly a 500 megawatt thermal instead of 2,000 megawatt thermal. So that's probably more or less enough more overview than any of you wanted on the actual devices. But what's again the motivation of HPC? How do we bring HPC to this problem? Okay, and we've had this project now going on its 6th year, I believe, or just finishing its 6th year. Called CASTLE, which was the first energy innovation hub out of DOE, dating back to 2011 or 2010. Doug's here somewhere. He can correct me on the dates. I've kind of lost track. Anyway, the idea, as part of that, we were really trying to advance the numerical modeling and simulation capabilities as applied to specific nuclear reactor design and operational problems, primarily operational problems. One of the parts of that is that we did some really high fidelity simulations of Westinghouse's AP1000, and it helps so much, man. Westinghouse is just shooting like a rocket. Right? Nobody reads like the Financial Times or anything here? All right, anyway. So we drove them into bankruptcy. But nonetheless, this was like a really big success. But the whole point is that we were actually able to use Titan at Oak Ridge and use some of our new simulation tools to do really high profile startup calculations. So startup, there's a very specific process by which a reactor is validated at its startup. And this has to do with licensing and a lot of other features I'm not going to get into. But they do obviously a lot of calculations, a lot of measurements to determine that the reactor can be started up. So one of the things we did is we took one of our high-resolution Monte Carlo calculation codes. It's called Shift, that was developed as part of Castle, and we did some really high resolution calculations. So we basically ran on effectively all of Titan's 18,000 plus compute nodes, ran 10 to the 12th of a trillion. I can never remember what actually the vernacular numbers are, but 10 to the 12th particle histories to simulate the really pin-by-pin detailed power history inside the core at fresh fuel. And we're able to actually resolve the uncertainties of a lot of their lower order perturbation measurements. And this was a big deal to them. They didn't think that HPC had any role. Even Castle itself has been primarily focused on what we call industry-level computing. In other words, they look at, to them, big computing is something on the order of 1,000 cores. 2,000 is getting really big, and something like Titan is like, well, that's for labs to worry about. So they didn't think that this was anything that could be useful to them at putting something on the floor. So this was actually a kind of a big deal in terms of motivating that HPC really could have a role in nuclear reactor design space and operational space. So one of the things we looked at is, in this idea of this 2012 call that was an industry-based call from DOE to get something on the ground in 2025, which sounds like a long time, but is actually a pretty aggressive timescale. What are kind of these challenge problems that they need to resolve in terms of design that HPC could help? Obviously, they're going to resolve these with or without HPC, but is there something that HPC could be used to help in terms of validation and uncertainty quantification and things of those nature? So basically, the idea is that what we're proposing to do is kind of use the highest resolution coupled Monte Carlo Neutronics and CFD. Those are the two primary physics models you need to model an operational steady-state reactor. And there's a whole bunch of features that we want to basically look at to try to provide validated data sets that can help be used to validate their small subcritical experiments, and also their lower order calculations to say that, okay, these things are ready for startup. All right. Again, we're not proposing to replace those things because that gets into a licensing snafu. Okay. No vendor is going to sit there and say, oh, well, we can't build this reactor without high performance computing. But can we actually say that we can aid and provide virtual experimental data that can help them in the design and certification phase? Okay, now getting more, I think I'm going to try to segue from that intro into the area where are we with regard to what can we do in compute challenge space. So to make this really clear, I used a lot of acronyms that probably no one else in the room understands so that I can talk a lot more. So anyway, so what this plot shows is again, the two primary components of doing operational reactor modeling. So I've got neutronics on the blue and computational fluid dynamics on the red. And this is a relative scale. So this is kind of, you can think of the petoscale. This is, you can think of this as being Titan or Mirror or something like that right now. Where are we right now? So HZP basically means hot zero power. That basically means startup. So the fuel hasn't burnt at all. There's no depleted isotopics or anything in there. We've got a fresh reactor. We've actually shown we can model that to almost full resolution. That's something we can do, and we can do it on existing petascale resources. Now, when we talk about going up to, getting into what we call hot full power or operational states, which means that there's actual temperature coupling, the reactor's running, it heats up, the interaction cross-sections for neutrons actually have a temperature dependence, so now there's feedback, things of that nature. So projecting forward, what is it going to take to be able to do kind of this like single cycle hot full power modeling? Well, we're looking at where Summit Aurora is going to be. So we're still at the petascale, but we're at the hundreds of petaflops as opposed to the kind of single and low double-digit petaflops we're at now. Moving forward on this same scale, and then on the red scale, we're looking at Reynolds averaged Navier-Stokes. We're looking at hybrid LES. This is kind of resolving turbulence. So when you talk about modeling critical heat flux, you look at how you're going to handle things like turbulent modeling at surfaces and things of that nature. And that's kind of what these faded areas or shaded areas are kind of indicating. Moving forward, obviously as a reactor runs, the fuel depletes, you're burning uranium, you're replacing it with fission products. Reactors operate typically on something like in an 18-month cycle. The idea is the longer they can burn the fuel effectively, the more electricity they produce, because bringing the reactor down costs money and time, and they're not actually producing electricity. The margins that those things are built on are very, very conservative. All right, so the idea of all of this extra computation is, can they reduce those margins, increase the uprates? That means they're producing electricity longer, they're burning more fuel, producing less waste. Unicorns and rainbows abound. So the idea being that what we're trying to do now is looking at doing a fully, actually modeling full depletion at this high resolution. Okay, now we're starting to get to where the requirements really do require exascale computing requirements. And now we go out to trying to model that full cycle, and we're clearly up into the exascale range. So using the best physics models we have available requires this definitely requires exascale computing resources for this couple problem. And this is more or less what I just kind of walked through. We can do quite a bit at petascale, but really to be able to do coupled high resolution neutronics with at least hybrid Reynolds average Navier-Stokes, large eddy simulation CFD, we really need exascale resources. And the whole point here is basically to provide virtual experimental data sets that can be used to validate these low order perturbation simulations. That's really what they want. They're running stuff on a much lower level. They're taking shortcuts. They're tuning data to experimental systems, which is all fine. Okay, that's part of the design process. But can they actually, given that they're not going to build some prototype reactor to generate a couple decades worth of data like we did back in the 50s and 60s and had access to, is there something else that they can use in place of that? All right, and that's what we're trying to argue that HPC can provide. We can provide effectively a virtual laboratory to provide that data. All right, so, and finally, what's really required for all these advances? Obviously, we need the exascale platforms, and we need the R&D to enable our current algorithms to scale to the new architectures. And that's kind of a segue point of where I'm going to talk about for the rest of my time. And if I need to sit down to go over, I'm not where we are in time, just throw something at me or yell or scream or oh, there. Wow, okay. I thought that was my shot clock. All right, anyway. Okay, so I wasn't, again, 100% sure of the room, so what I wanted to do was actually do kind of a little cartoon here and talk about what are the real challenges. We all talk about, well, this is hard. Why is this stuff hard when we talk about moving to some of this new architecture space? All right, because Lord knows any of us would love to basically scale up what looks like an Intel Xeon, and I'm not trying to be pro-Intel compared to other people in the room or anything, but something like that forever, right? But power requirements are dictating that we have to, that we're moving to something that's more heterogeneous. So let's see, what does an actual Monte Carlo Neutronics method look like? And the cool thing about this, visually this is really, really simple. All right, this is actually kind of what a nuclear reactor looks like, idealized. It's not a full one, but basically we put uranium or plutonium or MOX type fuel rods. They're clad in water and they're put in this kind of big lattice. And minus a lot of little details, that's kind of what it looks like. All right, so how do we simulate what neutron transport looks there at high resolution? Well, it's pretty straightforward. We can sample a starting neutron. So let's say we sample a position and it starts in the fuel there. We basically sample some distance to collision, all right, which is basically built on solving different parts of the neutron transport equation and then sampling that. I'm highlighting this part in red for a reason that we'll get to later, because that's kind of where the complexity comes in. All right, that's where the physics are. All right, then we also calculate, well, what's the distance to potentially the next boundary? Then we determine which of those things are shorter, right? And then we push the particle that difference, and we tally the various state data that goes on. So for example, if we were interested in the neutron flux, which is a component of any neutron power array, the power that's going to be here, we would actually add up all those contributions. And then it's we process that collision site, which means sampling the nuclide, sampling the reaction, and processing the reaction. It seems pretty simple, right? And then we just wash, rinse, repeat over and over and over again, and we accumulate statistical quantities or statistical averages of all these quantities. So in concept, this is very simple. All right, why is this really challenging when we're talking about moving to these complex heterogeneous devices? Well, first of all, obviously this is a stochastic method. That means all these independent random walks are not really amenable to SIMT type algorithms, right? Because everything by definition is doing something else that's based on a random distribution of variables. All right, so achieving on-node concurrency is difficult. And then this is the real massive fly in the ointment. That little red sigma that looks simple and that other thing, that's sampling this. Okay, for example, that's basically the neutron interaction cross-section for uranium-235. So it's got all this, and here's a highlight of it, it's got all this awful-looking structure in it. The data sets are large. Okay, so putting all this data in memory so that you can sample it is about 1 to 5 gigabytes if we just put it into memory per temperature point. Okay, we need multiple temperature points, obviously. By definition, you're also randomly accessing all this data. You're not actually accessing it in a way that you can deterministically set up. And so we've got all this structure, and that really creates a nightmare in trying to do, to vectorize, if you will, these types of, both vectorize the operational flow of your algorithm and then manage the memory access patterns. So, what are the kind of algorithmic approaches? So what I have on the left there is kind of this standard way, and that's what the cartoon showed of how we've been doing this on kind of MPI-based communication algorithms. Basically, you basically parallelize over particle histories, and we do more than that in detail, but the devil's in the details there. But fundamentally, it's a simple kind of a linear flow where a particle's born. You look, okay, I'm calculating a distance to collision, distance to boundary. You choose one or the other. If it's a collision, you process the collision. If not, you walk to the boundary. You go through the process the surface, and then you kind of repeat. There's another way that you could, this is very clean. It's very easy to follow. However, it's not very vectorizable. Okay, so if I have something like a warp with 32 threads that all want to execute the same instruction at once, it's not very easy to see how you're going to get tons of performance out of that. So another approach is to say, well, instead of doing that, why don't I actually recast this algorithm based on the events? All right, so for example, I say, okay, I've got a bunch of active particles. I'm just going to say, I can calculate my distance to collision and distance to boundary for all of them. Okay, that's a common instruction, so I'm running the same instruction. Then I sort them based on what they're going to do. So I'm going to have a group of these particles that are going to go to boundary, a group that's going to go to collision, all right, and a group that may end up going off node or something like that. All right, so I sort them, and then I process that vector of boundary particles in a kernel. I process all those collisions. And then now I have something that looks much more vectorizable. All right, so ostensibly you can actually get vectorizable performance on that. Unfortunately, like everything in life, that doesn't seem to work on the newer architectures. And so get to why, but current progress. So we've actually implemented these internode kernels on both NVIDIA GPUs and on Intel FEs for the Monte Carlo Neutronics. We've actually got the early results, and these are not necessarily optimized yet. The first thing is, can we actually get these things on the devices now? Can we actually start looking at the performance and optimizing them? So I'm going to focus more on kind of the GPU, talk a little bit more about the GPU performance because we're a little bit ahead there. So obviously, in this room, everybody knows in the GPU, there's groups of 32 threads or warps execute together in lockstep. Basically, what we have found is that low-level divergence is really not that big a performance issue right now, whereas high-level thread divergence is basically always detrimental. Where things are really, really going to hell quickly is in memory access and memory patterns. Seems to be much more important to performance. So one of the things we decided to do was say, okay, this is the standard simple history-based algorithm, and literally that's what it looks like on the left. Do I get an award for actually showing code in this meeting? Has anybody done that yet? Checking. Anyway, on the right-hand side, what we do though is we can say, instead of just going through and running all particles from beginning to end, let's actually take these. Let's not sort after every event, but let's sort after a certain number of collisions or a certain number of events, just to simply improve occupancy, to give, basically to keep things in memory so that the warps have more things to work on every given step. And in doing so, we've actually seen that we've gotten a significant is in the eye of the beholder. We actually have gotten some performance out of the GPUs compared to just running straight multi-threaded on a node. This is basically on an Intel Xeon machine with, it has actually 3 GPUs. It's a little development blade. But we actually are seeing some, so the question is, how do we, and I'm not going to get into this because I'm running short on time. One of the big questions is, what's the fair comparison? Like, for example, for on-node performance, do you compare just running on all the, your best algorithm on all your available CPUs on node and compare to what you would get if you ran on the GPUs or not? There's some argument here. What we've decided to do is, if we basically run across our most optimal multi-threaded version of our algorithm on the CPUs and then just basically compare to the GPU, we're seeing something like a 2 to 3 times speed up over in that case. Obviously, we want to do better, but we're still really just getting started here. Okay, so we've actually, as I mentioned earlier, we've implemented both this history-based and event-based algorithms. One of the things that we found is that our modified history-based still it outperforms the event-based algorithm by a factor of 2 to 3, and so we're like, well, why is this? Because it should be much more vectorizable than the other one. Well, the reasons are that low-level thread divergence just doesn't seem to be as big a deal on the GPU, although I think it is on the FEs. But another big thing is sorting ends up being a dominant cost. Just doing these sorts all the time ends up really overloading your performance. And then, of course, the big one is memory access and fetching, and that is sorting over more events creates additional indirection in your vector. Okay, and when and basically being able to do memory prefetches that are warp local is where a lot of your performance, or where we're seeing a lot of the performance comes from. So that's, I wish I had some more numbers to put to that, but I don't right now, so we'll just let that go. Second to last slide. Basically here, what we're now doing is, this stuff was all done. Remember I showed you all that complicated energy structure? This was actually done using a reduced order approximation to that we call multi-group, where we actually break that into a couple groups. When we actually go into the real detailed energy structure, it creates the even further challenges that we're trying to deal with right now. And a lot of it is that when we're in the real physics, you have all this low-level thread divergence that is so much higher in continuous energy that and has so many more interaction channels that that low-level thread divergence is percolating up and really causing bottlenecks in performance, so that we're now looking at oversubscription methods where we're actually oversubscribing multiple particles to single threads to try to address this. That's kind of where we are now. I know that was probably a fast overview. I hope it wasn't too fast, and there was something, at least one or two things useful out of here. But I'm going to just finish there with 1 second left. So, okay. Thank you.
Just one quick question.
Yeah.
Did you want to say a few words about your performance on the PHYs at all, or?
No, because it's really bad. I will. What we're seeing is basically we took where we are in the fees right now is we basically put our OpenMP threaded version of the application on there. So the advantage of the fees is if you have a threaded application, especially if you're using something like OpenMP or OpenACC, you can drop it on there very quickly, which is nice, which you can't do as easily on the GPUs, just because you have to manage those memory transfers one way or another. The problem is, so you can get it on there and running, but the performance is terrible. All right, and so what it seems, my early conclusions is our initial implementations are something like 4 to 6 times slower than just running straight up on the Intel Xeons. All right, so it's about 4 to 6 times slower. What we're seeing is that, as opposed to where I mentioned here, where the low-level thread divergence is much less important than the memory access and prefetch patterns, on the feed it doesn't seem to be as that in that way. And maybe some people here could comment, but it seems to me that to get the software thread performance, the compilers are doing a really bad job right now of vectorizing code, in the sense that we have operations that look like they should be perfectly vectorized, and the compilers are just not vectorizing the operations, and there's no way to tell them to.
Are you hopeful about the night's landing, or?
Well, we're hopeful, right? Yeah, but.
So Intel folks here take note.
But.
There's a question right here.
Number 1, PHYs. Here comes the mic.
Oh yeah.
Did you try to talk to the Intel developers on that problems? Because that's really the first one I heard. The compiler is bad in report telling you why it's not vectorizing.
Well, this is just what we're seeing kind of out of the box right now, is that we have blocks of code that look like they should be vectorized, and it's not being vectorized. Yeah, so yeah, it's been being reported, yeah.
Have you taken a look at the vectorizer report?
Oh yeah. So. Yeah, I mean, the bottom line is it's just not, but the compilers aren't doing it. So I don't, we can say it, that's how we know it's not vectorizing the code. But I mean, at the same time, I don't know how to make it do it right now. But I'll be honest, we have a group I've been working more on the GPU side personally, so I'm not 100% sure where our team is on the.
From a NASA perspective, I'll also say that the Knight's Corner has not been a good system.
Yeah, and this is all on Knights.
Knows about this very well. There's a lot of, like he said, there's hope that the Knight's landing is going to work, but.
Have you already access to the KNLs?
Yeah. Right now, I will say that on the Knight's Corner, these are all the results I just mentioned were Knight's Corner. They're not obviously not Knight's Landing, and so this is still very early in that regard.
Any other questions?
Yeah, real question that I had earlier. Is the simulation for the whole reactor or for the complete reactor, so you don't do any simplifications like using symmetries to cut down on the necessary?
Right, so a lot of the stuff we do is in what we call quarter or rotational symmetry. So, for example, a lot of the fuel shuffling patterns they actually use what looks like a rotational symmetry, so that if you rotated the core around, you actually have some symmetry there. But part of the things that they want to look at in the full core as the core is burning is that they actually have these small variations in non-symmetric regions of the core, which is ultimately something that they actually want to look at. That's part of the challenge problems that we actually have to try to resolve. So.
And the other question that I had, why do you have so much turbulence in the reactor? Shouldn't that be...
So much what?
Turbulence. You were talking about large eddy simulation.
Right. That's basically, so one of the basic challenge problems is to resolve critical heat flux at the surfaces of the fuel clad, or at the surfaces of the cladding interactions. All right, and so that's basically where that's resolved. Most of what they're doing is not large eddy simulation. Most of it is RANS. So basically, you just run LES on a few small regions of the core. So it's a hybrid method. Yeah, obviously, reactors being turbulent would not be a good thing. Yeah.
There's a question there.
To be honest, 2 comments, okay? Turbulence is good. It enhances heat transfer. So you want turbulence. You don't want too much turbulence. So that's the challenge. You actually try to swirl. There are grids that purposely swirl the fluid around the rods. So you want to get enhanced heat transfer. So it's kind of a slippery slope. Also, I add from the ECP point of view, Tom's project is very typical of what the application projects are doing right now. He mentioned a milestone. So they're down working close to the metal, porting code, trying to understand what's working and what's not. So, I mean, this is a great example of what ECP is doing with the application. So I think Tom's at a point now where he can, you're ready to interact more closely with vendors and try to understand, what choices he needs to make algorithmically and in data structures, et cetera, to ensure performance portability, which is, admittedly more of a journey than a destination, right?
So the performance port, I didn't really bring that up here. I don't know, did Paul talk about performance portability? And that's going to be probably the single biggest challenge in here, because one can envision using some sort of programming model so that the code looks the same on both, but the reality is, given the differences on requirements, we're not going to see the same type of algorithm perform the same way on, even if it's written in a language agnostic manner.